So you have the title of the slide. Every word is there for some reason, except the in maybe. But so I'm going to talk only about symmetrical equilibria. Scalar, this is an important word. Two-person, not very important. Infinite horizon, very important. Linear quadratic differential game. Scalar, you know, this theory had to arise in economics, because control theoreticians, among which I am, would never bother about such powerful theory as the linear quadratic theory for a scalar state problem, you know, so-called monovariable system. The linear quadratic theory was invented to regulate complex systems, not scalar systems. But economists have these small models with a scalar state, and without the scalar state, nothing of this holds. So, very brief outline. I will say just one word about the history of the topic. I will summarize the technique of Tsutsui and Mino, making it more compact maybe, and it's why I criticized it, its shortcomings. One word about the problem considered by Rowat, and I will make a detour by the problem of the choice of admissible sets of admissible feedback strategies, which is an old problem in differential games. And then I will devote the rest of the talk to slightly more general STS-INQDG, as you are about to see. I mean, symmetrical, two-person, scalar, infinite horizon, linear quadratic differential game. Classical analysis, which you all know, Riccati equation and the like, Rowat's piecewise affine strategies, other nonlinear strategies very quickly, and a short conclusion. So the inventors of this whole story were Tsutsui and Mino. I will refer to them as T and M. In this paper of 1990, so that's 34 years ago. And a notable follower was this paper by Rowat in 2007, which I will also comment upon for the history itself. So let me summarize the method invented by Tsutsui and Mino. You know that the stationary HJCIBC equation, so let's become on this HJCIBC. William Hamilton introduced it in optics and mechanics to unify optics and mechanics with the Hamilton minimality hypothesis. Jacobi studied the equations simultaneously. Constantin Carré-Théodory was the first to use it in calculus of variations as a sufficient condition of optimality, essentially the same thing as the modern use. This was in the 1920s. Rufus Isaacs discovered it independently, ignoring Carré-Théodory in the context of two-person zero-sum differential games. Richard Bellman invented it almost simultaneously with Isaacs, and they were not friends with each other. Leonard Berkowitz had a funny story about their interactions. And as far as I know, Jim Case was the first to use it for nonlinear, for the Nash equilibrium of n-person differential games. Well, anyhow, if you have a exponentially discounted payoff, you know that for the infinite horizon game, you take the value function, Isaac's value function, as a discounted function of x only, and you get an equation which looks like my equation 1. H is for Hamilton. Then you differentiate it with respect to x, both sides. You call y prime, w prime equal y just as a shorthand notation. And differentiating, you get this equation where y of x, w prime, is obtained by differentiating h. And I call f, this novel equation, f of x, y, and y prime. Equals 0, by the way. I'm sorry, equals 0 is missing here. Now I insist that the condition f of x, y, y prime equals 0 is a necessary condition but only necessary for y of x to be a valid W prime solution of 1. Then they find, Tsutsui and Mino find the first integral of the equation f equals 0. And this first integral, which has an arbitrary a constant c here, gives a family of function y equal h of x and c, where c is a constant. Now the question is this constant arbitrary or unknown? And just as a reminder, let me say that. Assume you have a condition, something like a of x equals 0 for all x in an open set. Then clearly this implies that a prime of x equals 0. But this is only a necessary condition. And if you integrate back, you get a of x equal constant. Does that mean that there are an infinity of solution? Of course not. You see, so if you differentiate, you get a necessary condition, you integrate back, and you cannot ascertain that the integration constant that you have is arbitrary. I say that because I've seen this kind of mistake in several papers. But Tsutsui and Mino don't make this mistake. And once they have this family of solutions of equation 2, which is f equals 0, I mistook here, they do the following. Let w tilde of x and c now be this function h, which is in my equation 1, taken at x and h of x and c. Now, because if you differentiate this, you find w prime equal f of x, h, and h prime. And because h is a solution of y equal, y, there is no equal 0, I'm sorry about what I said. Because this function h is a solution of the equation y equal f of x, y, and y prime, then you can conclude that this w tilde prime is h of x and c. So you plug this back in equation 3, and you see that indeed w tilde of x and c satisfies equation 1 for all values of c. So there are actually an infinity of solutions, but this is not surprising because in equation 1, I did not write any boundary condition. And everybody knows that a differential equation, or even worse, a partial differential equation without boundary condition has an infinity of solutions. The question now is, do they generate equilibria of the game? Tsutsui and Mino apply this on this game, where their state is P, their dynamics is this, where U1 and U2 are the controls, P the state, A and S are positive constants. And they have profit that they want to, both players want to maximize, which is given by this. This is a microeconomic problem that many of you will recognize, but I choose not to dwell into the economic meaning of these things. I will stay a pure mathematician almost. Now you take this problem, you write its Hamilton-Jacobi-Isaac-Spellman equation, you get this, and the optimal control is not quite what I wrote here because it has the constraint that all variables are non-negative, therefore the U should be non-negative, and therefore this is the minimizing control only if phi is positive, and if phi is negative, if this formula is negative, then the maximizing control is 0. Now, they differentiate, as I say, they differentiate this with respect to x, and they find this equation, which I called capital F, and they find a first integral of capital F, which is what I wrote here, y minus beta for some beta, minus k1 p minus alpha to the power gamma, times the same thing with a k2 to the power 1 minus gamma equal a constant. And if you try to place this in the equation and try and see what you need for this to be a solution of the equation we had, you see on the one hand that K1 and K2 need to be the solutions of this Riccati equation, which is the classical algebraic Riccati equation associated to this game. And you find also that, well, I'll come to it later, excuse me. And now if you try C equals 0, then you need that either of the two coefficients of the two terms be 0, and therefore you find y as a fine function of p, which I wrote here. Or you try what happens if c is not 0, and then you have curves in the py plane, which I'm going to comment upon. The py plane is the classical plane used by calculus of variation. They say that they lift the problem in this plane. So this is the drawing. So excuse me, it's a bit messy, but okay. This is the p-axis. P is the state. This is the y-axis. Y is the costate or w prime, the derivative of the value function. The red line is the line which limits the u positive. To the right of the red line, the controls are positive, so you don't want to consider what happens to the left. The blue line is the line where p and y are such that the function phi, which I show, is 0. Therefore, when you are to the left of the blue line, the state moves to the right. And when you are to the right of the blue line, the state moves to the left. Now, the big thick lines are the solution phi equal a fine function of p. And I drew them almost correctly, corresponding to Tsutsui and Mino's problem. And the thin lines are these famous lines y equal h of p, which are solutions of the differential equation coming from the first integral. Now, if you look at those which are below the line k1p here, you see that they define a function y equal h of p only between my little circle here and the limit u equals 0. Because afterward, here you have a vertical tangent and the curve goes back to the left. And so it's another function if you wish. So take the piece which is correct, which is between the circle and the red line, and the dot is the steady state if both players use the strategy phi, because the state moves to the left until you reach this dot, and on the other side, it moves to the right. Now look at the curves which are above the K2 solid line. They seem to define a function h equal y of p over the whole p-axis toward plus infinity, because they are asymptotic to the K2 p equal K2 y equal K2p line, so it goes arbitrarily far to the right. But in fact, you cannot use them so far, because you need to, for the theory of Tsutsui and Mino to work, you need to have a system which, when you use the equilibrium strategies, is stable. So you want the state, if you pick this line here, you want the state to converge to the dot, but each of these lines will intersect a second time the blue line. And my drawing is not very clear, but because the blue line has a slope less than the line K2, and these curves are asymptotic to the line K2, they will intersect a second time the blue line, and beyond this intersection, the system driven by the strategy phi is unstable. It diverges to plus infinity, and you don't want the value function to diverge to plus infinity. Therefore, you can use, although these lines define a function y equal h of p over the whole axis further right to the point u equals 0, still you can use them only in a compact interval. So this is a problem now. The first, the curves coming from the first integral found by Tsutsui and Mino are usable only over a compact interval of the axis R to R plus. Okay, call L one of these intervals corresponding to one of the functions H, and call T sub L, capital T sub L, which is a function of initial state and of the controls. Define this as being the first time instant when the state leaves L. Tsutsui and Mino surreptitiously changed their problem to the new one, which I wrote here. Pi I equal sum from 0 to TL of the same criterion. This equation is hardly visible in the article. It's not even numbered. You cannot refer it by its number in the article because it's not numbered. But okay, that's the problem that they consider. So for that problem, they actually find nonlinear Nash equilibria. However, this is a very different problem from the original one. This is what's called the free end-time problem, because the end time is defined when the state reaches a target in the classical parlance. These targets are the two extremities of the interval L. So this is a very, very different problem. I don't know what meaning it can have in economics, but I don't care today. The problem is that in all the discussion in the original article, the authors insist that they solve an infinite horizon game, and that this feature explains many peculiarities, including the existence of many equilibria. And I quote one of the many sentences to that point. So I quote here in purple. Purple is a color that I don't like. They write that for each price between this and that price, there exists some stationary Markov perfect equilibrium which supports this price as its stationary price. And readers, of course, were led to believe that this applies to the infinite horizon game, as they claim, and many have used it as such. Now, the correct statement is the following one. For each price strictly between these two prices, there exists a free and time game with a Markov perfect equilibrium which supports it as its stationary price. But of course, the game you consider is a function of the price, of the stationary price you are considering. It's not all the same game. Moreover, if you take a price very close to one of the ends of the interval, the state, the prices interval within which the game is played may be very small. So that's what was the situation when I got interested in this. But now let me say a word about the problem considered by Rowat in his 2007 article. So his problem is this one, which I wrote here, x dot equal minus delta x plus u1 plus u2. And his criterion is GI equal minus this positive integral that both players want to maximize again. You can write in Rowat's article, there is no misleading statement. He doesn't claim that he does, well, that's really the game that he considers. There is what I call a misnomer, because I claim that what he shows are not Nash equilibria. And the reason is that he uses the theory of Dockner, of the book of Dockner et al., which is a good and well-known book, which uses this concept of feasible strategy pairs. What is this concept in game theory? Well, in this approach, to investigate the optimality of a strategy, and equilibria are about optimality, to investigate the optimality, one only considers those comparison strategies that fit well with the opponent's strategy. And you just ignore those that you don't like. So of course, you have optimized among, you don't know how many strategies, maybe very few. Incidentally, this concept was first introduced by Justin Blaquière, Françoise Gérard, and George Leichtman You can find it in their 1969 book, Qualitative and Quantitative Game. Actually, it was in the PhD thesis of François Gérard, who was a student of Austin Blaquière. Austin Blaquière was a friend of mine, and like mine is somebody for whom I have great respect. Well, they used that because they wanted to make a theory directly in terms of state feedback strategies. And so they had this old problem of knowing what are the sets of admissible state feedback strategies. So I make a detour by this problem. So I stay within the context of two players game just to make things simpler. You want to be able to write something like that. But if you don't say what is this set's capital phi 1, this has just no meaning. If you say minimum over phi 1, but you don't say over which sets, maybe you tried two of them, you chose the best, and you have minimized. So you have to say over what set. But now, what are the good sets phi 1 and phi 2 is a complicated question, as many of you know, because we have no nice theorem guaranteeing existence of a solution to the differential equation driven by these feedbacks, allowing such things as a bang-bang control. You know that the only two theorems we have is either function Lipschitz continuous or the Peano theorem with right-hand only continuous, but then you don't have uniqueness, and anyhow you need continuity. And experience shows that there are games where you want to use, for instance, bang-bang controls, which are not continuous. This has been this has caused a large flow of literature, and I quote just a few: Wendell Fleming, the best of these papers as far as I am concerned, Avner Friedman, Nikolai Klasowski, and Andrei Subbotin in their book Differential Games, Emilio Roxin, Pravin Varaya, Leonard Berkowitz, and others probably. More recently, Florian Wagner sent me a preprint with Nico Jacola, yes, Nico Jacola, I think, where they attack again this problem using Filippov solution of differential equations. We may discuss it later, Florian, if you wish, but I have the feeling that you still need to exclude from the set of allowed feedback strategy the exceptional sets, denoted the capital E, which depends on the opponent's strategy. So it's still not completely solved if I understood well.
By the way, Pierre, Nico is presenting this paper next week.
Okay, very good. Very good. They sent it to me. So, but did not spend enough time on it yet. Back in 1992, in a lecture in Italy, which was published by the Italian School of Dynamic Games, I proposed a way which I do not solve this whole problem. I don't think it can be really solved. But I proposed a way around it. And this is the way I proposed. We want the sets of admissible strategies to have the three properties which I wrote here. They need to be closed under time concatenation. Otherwise, you don't have dynamic programming, you don't have the Isaacs equation, you don't have Pontryagin principle either because you don't have strong variations and so on. You want them to contain admissible open loop controls, by which I mean that the players are allowed to just ignore the states. And of course, the difficult point is that you want them to be compatible in the sense that if you pick any strategy in phi 1 and any strategy in phi 2, the differential equation has a solution when it is driven by these two strategies. And the payoff is defined. I state the following theorem. If you can exhibit phi star 1, phi star 2, which are compatible with U1 and U2, I mean that each of them opposed to an open loop control gives a solution to the differential equation. And you can prove this where you see I use only open loop controls as my comparison controls to talk about optimality, and symmetrically for phi2, of course. Then 1, I said that phi1 star and phi2 star are a Nash equilibrium pair of strategies over any pair of admissible strategy sets that contain phi star 1, phi star 2, and satisfy the 3 conditions. And 2, there exists such pairs of strategy sets. Nothing very original, because again, I don't define explicitly what are phi1 and phi2. But at least I say that if you use open loop controls as a comparison controls, you can ascertain that the phi1 star, phi2 star that you have exhibited are the equilibrium strategies of a Nash equilibrium. You don't know, and these sets exist. Characterizing them is just too difficult. Or of course, you could say, oh, I take for phi2, the capital phi2, the set of all that are compatible with phi1 and so on, but this is not constructive either. Okay, that's it. I will now proceed to the second part of the talk. And I warn, this is work in progress. Yesterday evening, I was making calculations with expanding an equation with 72 terms, which is probably one of the most massive I ever did. But let me go ahead. So I define a symmetrical two-player scalar infinite horizon in arithmetic differential games by the following equations. My state is x in R plus, so I have positive state. Bounded controls, positive between 0 and capital U. 2 players. Dynamics affine in state and control, but as general as possible, symmetrical, but as general as possible as a affine dynamics, and a criterion, which is as possible as I can for a quadratic criterion. Of course, you do not need constant terms because they play no role in the optimization problem. And just notice that I picked a positive R, positive Q, so I will minimize a convex set. You know, the great divide between economists and mathematicians and control theoreticians. Economists maximize concave functions. Mathematicians minimize, economists maximize concave functions. Mathematicians and control theoreticians minimize convex functions. This is the great war, and of course, we are the good guys in this war. There's no such thing as a theory of concave sets. So I like convexity. But of course, it is exactly the same thing. By the way, if you go back to, if you go back to this Rowat's problem, this is explicitly minus a convex function. So maximizing minus something, it might be simpler to say that you minimize the integral. But okay, who cares? I just mentioned that the 2 problems I quoted, the one by Tsutsui and Mino and the one by Rowat, fall under this general framework with the choice of parameters, which I wrote here. Some of these zeros are really meaningful. This 0 is what ruins Tsutsui and Mino. And the 2 zeros that I see in Rowat's line simplify considerably the problem. Now, first obvious proposition, because I have bounded the controls and because my differential equation is a stable system, then the state remains in a compact set. The state is bounded. And if the state is bounded and the controls are bounded, the integrand in the cost is bounded, and therefore the criterion Ji is well defined, and later on my value function will be bounded. By the way, if Rowat had bounded this positive control, maybe well, maybe the paper is completely correct. I still have some doubt. Okay, you can write the Hamilton, Jacobi, Isaacs, Bellman equation of this more general system. This slide is used only for two purposes. One is to insist on the fact that I have two forms of the Isaacs equation. The top one that Isaacs calls main equation 1, and the bottom one that Isaacs calls main equation 2, and I will use both. And also you see what is the minimizing control if it is positive, and the minimizing control is 0 if phi is negative. Now, a word about the classical analysis of this problem. You all know that you can look for value functions which are quadratic functions in the state, and you can a priori find two of them because K here should satisfy the algebraic Riccati equation. And I also wrote the formulas for L and M. The formula for L is ugly, although the denominator might be simpler than that. The interesting point is that the equation for M implies only L and L square. Oh, I'm not sure I really need this. Well, D stands for the determinant of the matrix of quadratic terms, and delta stands for the discriminant in the algebraic Riccati equation. That's where the fact that the problem is scalar is absolutely of the essence, because it's for that reason that you can explicitly solve the algebraic Riccati equation. I tried to see if I could do it for a 2x2 system. And you can do something, and I end up with a 6th degree algebraic equation, and only for a 2x2 problem. 3x3 would be just horrible. So now I define two special states. The first is my x hat, which is L2 minus L1 over K1 minus K2, where K, oh, I'm sorry, I made a mistake. Where L1 and L2 are the coefficient of the linear term in the value function. So this choice is actually is for that purpose, that it makes K1 x hat plus L1 equal to K2 x hat plus L2, which means that the gradient of the value function W1 or W2 are the same. Therefore, the strategy phi I are the same. Because the strategy depends only on W prime. So at x hat, phi defined by W1 or by W2, which I will call phi 1 and phi 2, are the same. The second special state is x-chech, which is this, which is chosen such that phi 1 of x-chech equals 0. Phi 1 is with the solution K1 of the Riccati equation, and I should have shown that K1 is the positive solution. Again, I make a mistake with the computer. Check. You see K epsilon 1 is minus 1. So K1 is with a minus square root of delta, but I have a minus before. So K1 is positive and K2 is negative. Okay, and I said earlier in defining the problem that I requested that the upper bound on the controls be at least as large as some U hat. Well, this U hat is just this, because I want the players to be allowed to use the strategy phi 1 or phi 2 at x hat. I also introduced new W functions. So we have already seen W2 and W1, which are the standard quadratic function with the two possible solutions of the algebraic Riccati equation. And I introduced a third one, which I call W0, which is defined in terms of psi, which is just the stationary point of the dynamics under zero control, and gamma, which is the ratio of the discount coefficient over the dynamic coefficient of the equation. Notice that both are inverse over time, so this ratio is dimensionless. Thus, it has a meaning to have powers gamma. So this function W0 is this, which you are about to write immediately. Of course, very simple, as you see, which depend here on W1 at x change. But actually, if you look at it, it's very simple. In particular, if you look at W0 at x change, which is where phi1 is 0, you have, yes, you look at x change, this ratio is just x change minus psi to the power 2, which cancels this one. Same thing here, same thing here. And therefore, you are left with, this is 1. So you are left with W0 of x change equal W1 of x change. Okay, this is written in the definition of W0. Now I define a composite function W and a composite strategy phi, which are as follows. W will be W2 if x is positive, but smaller than x hat. It will be W1 if x is between x hat and x change. And it will be 0 if x change is, if x is larger than x change. So just for the, to be nice, I will state W phi 0 of x equals 0. But okay, that's just to have a single formula phi sub L of x of x. Now I have to impose 3 conditions on the parameters of the problem. The first one is phi 1 of psi positive. So I recall you that phi k1 is the positive solution of the algebraic Riccati equation, and phi 1 is decreasing because you have, in phi 1, you have a minus k1x. So phi 1 is decreasing. So if at psi it is positive, where it vanishes, x change is larger than psi. The second condition I have to impose is phi 2 of 0 positive. This is because you want phi 2 to be an allowable, an optimizing strategy from the state 0 up to x hat. This condition you find in the paper by Rowat, by the way. It's there. And the condition 3 is more complicated, and I've been working on it last week. I wrote it that way. This is actually the derivative of the function phi if you use W0 as your W in phi. You remember that phi is B minus whatever R, B times W prime plus Sx minus R. So this, oh, I'm missing a B in front of my W0 here. Excuse me, I'm missing a B. This is BW twice derivative 0 of x change plus S positive, because this is the derivative of the function phi. Actually, I can find that if this is true, then it holds for any x larger than x change. And this guarantees that phi will remain phi as constructed with W0 in, for W prime, will remain negative, and therefore 0 will be the minimizing control. it's difficult to analyze, and I'm still not completely finished with that. Now I state the theorem. One, the composite function W is continuous and continuously differentiable, which is a bit of a surprise. And under my conditions 1, 2, and 3, the composite function W is a value function of a Markov Nash equilibrium with the composite strategy phi as equilibrium strategies. So this is Rowat's piecewise affine strategies, which are new with his paper, which I've never seen elsewhere before. Let's prove this theorem. Continuity at x hat. I claim that for all x's in real x's, the difference W1 of x minus W2 of x, remember these are the quadratic value functions, the classical quadratic value functions. Their difference is 1/2 k1 minus k2 times x minus x hat squared. To tell the truth, I first found that by direct calculation with this horrible formula, and it looked like magic. But actually, it's very simple. This is the proof. We have seen that we have chosen x hat in such a way that the gradients W prime are equal. W prime 1 by, and W prime 1 and W prime 2. Now, both Wi satisfy the HJIB equation, which give you W in terms of W prime. And therefore, if the two W prime coincide, the two W coincide. And therefore, the function is the W, the composite function W, is continuous at x hat, where you change from W1 to W2. Therefore, the function W1 minus W2 is a second degree polynomial in X with leading coefficient K1 minus K2 over 2. This is because each one is K1 squared over 2 plus. And second degree polynomial, which vanishes together with its derivative at X hat. Therefore, it is this polynomial X minus X hat squared. Now you can do the direct calculation if you like. You might not like because it's a bit massive. But it's not that complicated because you see, if you write W1 minus W2, remembering that each one is 1/2 K1 Kx squared plus Lx plus M, you have this Ky minus K2 times x squared minus this ratio 5 times x, but this is x hat. So you already have x squared minus 2x hat x. So that's the beginning of the expansion of this x minus x hat squared. So you are left with showing that this last term, 2m1 minus m2 over k1 minus k2, is equal to x hat squared. Therefore, this L2 minus L1 over k1 minus k2 squared. But this is not so complicated because you have a k1 minus k2 that you can drop off on both sides. And I insisted on the fact that M1 and M2 are a function just of L. M is a function of L squared and L. And when you make the difference, you have an L2 minus L1 that factors out. And therefore, you can also simplify by this factor. And you are left with proving this, which is a big calculation, but that you can do. So it's not too surprising. But of course, the good proof is the abstract proof. Continuity at exchange. I insisted when I showed the function W0 on the fact that at exchange it coincides with W1. Therefore, this is fine. Now, how did I construct this function W? Well, that's simple enough. I recall that I assumed that phi1 of xi is positive and phi1 is decreasing, that I know that xi is larger than exchange. And W0 is my W function only for x larger or equal to x stretch. So they are larger than psi. Therefore, if you use the strategy 0, the state moves to the left. So I integrate the differential equation with control 0 from an initial state Tx written here in red. So the state decreases. It reaches x stretch, which is the limit of the area of the region where I want to use W0 at a time which I call T stretch, which is characterized by the fact that the linear differential equation reaches x stretch. Then I define W0 this way. I take e to the minus rho t W0 of x, the initial x, as the integral from t to t stretch of the integrand taken when u equals 0. So the terms in S, R disappear. And I integrated here only up to t stretch. So I add the value from t stretch to infinity, which is just this thing, e minus rho t stretch, W1 of x stretch. So this is exactly what I did, and it gives the function W0, which I showed. But since W0 is defined by this integral, this implies that it satisfies the Hamilton-Jacobi-Isaacs-Bellman equation with U1 equals 0. And now, if you use the first form and not the second of the Hamilton-Jacobi-Isaacs-Bellman equation, you see that this implies that the derivatives of W0 and W1 coincide at x stretch. So again, you might do it by direct computation. It's not as complicated than for the first one. If you take the function W0, which I showed, you differentiate and you look at it at x stretch, and you find this. And yet then you use the fact that W1 satisfies rho W1 equal, you know what, the Hamilton-Jacobi equation, then you find that this indeed is W prime 1. Therefore, at this point, I have a composite function W, which is continuous and continuously differentiable. Now I need to show that indeed it is the value function of an equilibrium. So thanks to the condition 1, phi2 of 0 is positive, phi2 is increasing, k2 is the negative k. Phi2 is increasing, and therefore phi2 minimizes the Hamiltonian over 0 x stretch, and this is the domain over which I wish to use W2. Because of its definition, phi1 minimizes the Hamiltonian over x hat x stretch. I chose x stretch precisely in order to guarantee that phi1 of x was positive in this interval. And my condition 3, which I said, again, I'm missing the B before W0 differentiated twice. I'm sorry, I need a B here. And because of condition 2 and the fact that this inequality is granted for all x larger than x stretch, and this is a somewhat tricky thing to prove, then I can conclude that if you, it's not phi1 here, I'm sorry, if you compute phi of x using W0 as the W that appears in the formula for phi, so it's BW prime plus Sx minus R. So if you compute phi, it's not phi1, with this W prime 0 in it, then this thing will be negative because this guarantees that its derivative is negative all along, and it was 0 at x stretch. Therefore, if it was 0 at x stretch and the derivative is negative, for x larger than x stretch, it's negative. And if this formula is negative, then phi 0, which is 0, minimizes the Hamiltonian. So now I know that my composite phi function minimizes the Hamiltonian over the whole half line 0 plus infinity. I know that my function W, composite function W, is C1 and satisfy the Hamilton-Jacobi Isaacs-Bellman equation. And I have the boundary condition. Because I bounded the controls, and because the equation is stable, the state is remains in a compact interval, and therefore my function, composite function W, is bounded. It's a continuous function of X, and X is bounded. Therefore, I have the correct boundary condition on W. So everything fits, and now we have the proof that I have a Nash equilibrium. Okay, I'll finish quickly. If I try to apply the method of Tsutsui and Mino to my more general problem, well, I do essentially the same thing as they do, but a little bit more general because I have coefficients which are not zero, while they do. In particular, I will come back to it. I can do the same. This is exactly what they do. This was the equation y prime equal f of y and y prime, y equal f of y prime and x, excuse me. This was my equation capital F, which is the same as the second line, provided that you choose x hat this way and y hat this way. But miracle, this is the same as the x hat I already showed. And so you can try the affine solution, and you can try the non-affine solution, the Tsutsui and Mino's first integral, which is this thing, where alpha is a number between 0 and 1, and it is exactly this, 1/2 minus 1/4 of rho over square root of delta. And you have essentially this drawing, which is now, you can think of this axis as being phi or minus y. It's not completely correct because phi is b times minus 1 plus sx. But okay, essentially it's the same thing. Both are linear affine in x. So you again have the two affine solutions. The nonlinear solutions arising from Tsutsui and Mino's first integral. What I claim is that the reasoning I had at xch, which is the place where phi 1 reaches 0, you have essentially the same at x tilde, where one of the nonlinear solutions arising from Tsutsui and Mino's first integral reaches the x-axis. And so you can, by the same trick, validate these non-linear strategies. Okay, let me conclude. So revisiting Rowat's article, provided one bounds admissible controls, and therefore do not have to care about well, you have solved essentially the boundary condition that you want the value function to remain bounded. One needs neither the equilibrium in feasible strategies, because I have shown that everything works well. He needed the feasible strategies to eliminate those that would cause the value function to diverge to plus infinity. But once you have bounded the admissible controls, it cannot diverge to infinity, so you don't need that. And the other reason for appealing to Dockner's theory was that he thought that he had an irregular value function. And Dockner et al. Have a generalized sufficiency theorem where they have a value function which is not C1. But this value function is C1, so you don't need it. I'm not quite sure that the necessary conditions for everything to work are satisfied in Rowat's paper. I'm finishing to check that currently. As I told you, it's ongoing work. The main difference with Tsutsui and Mino is that they were unlucky and they had the wrong sign for the determinant of the matrix of quadratic terms in the payoff. It was negative, and therefore their two solutions of the Riccati equation have the same sign, and this is what ruins their analysis. So it's just bad luck, yet I say they remain the inventors of this whole theory. It's just too bad that they misinterpreted their results. Thank you.